Hi, I am Cinthya Aguilar Diaz. I'm from TM 401, but I am taking again the subject of secondary manufacturing processes. I'm going to explain the integrative project that is joining a door and a sub-assembly frame by welding and adhesive bonding. The introduction. In this project, I'm going to determine the correct procedures and cost for processing a joining a door, of the process of joining a door and a frame by welding or adhesive bonding. It's important to have a correct design and control of all the factors and variables that involves every final product. So the study of the design and the factors is very important. The case statement, a frame door and a car will be joined, is intended to know the process and cost of them. This is the design of the frame. This is the design of a typical door weld. It has a lot of joints, well, a lot of points to weld. The proposal of a possible solution. The different components involved in this frame assembly, in addition to the different weld joint types and material thicknesses, are shown in this table. You can see the part ID. The part ID is how they identify each part of the design, and the component name, the thickness, the joint components, the weld type, the weld length, and the weld in inches, in centimeters and in inches. The type of welding that is intended to be used is the MIG. The suitable welding conditions like weld wire, feed race, shielding, gas flow rate, and welding current are shown in the next table. Here we we have all the data and all the conditions that this MIG weld must follow in order to accomplish with the welding of each part, part 1, part 2, part 3. All is everything is made. So based in the previous table, the total of consumables in terms shielding gas in cubic feet, the electrode wire in labors, the electric power in kilo can be computed. Also, it's needed to calculate the costs because these are very important in every process. So with this information, it was calculated the hour production, the vehicles per year, the typical robot efficiency, the labor wage. All this was calculated. The proposed layout. Here are operators, the MIG welding robot, the handling robot. And for the standard door, it was done the same. And this door will be made by spot welding and adhesive bonding. The adhesive bonding is applied at the hem flanges that join and the inner and outer panels. Here are the material, the thickness, the thickness of the material, the recommended electrode, the fused zone, the flange overload, the spacing of the spot weld. Here are the shear strength of the aluminum, the carbon steel, the stainless that are going to be taken in account in order to calculate the parts. So the spot welding design guidelines in regard to electrode diameter, spacing, and flange dimensions are shown here. So with the data that was shown here, we can calculate the parts. We can calculate the considerations that, well, the data and the, for example, the recommended electrode, the fused zone diameter, the recommended flake overlap, the recommended single spot spacing for each part of the design. Now, also was calculated the costs of each of all the of all the things that are necessary in this process. So the analysis and argumentation and explanation of the results. So why these results are correct in this part are going to be explained. The manufacturing activities are divided into manufacturing system and operational level. In the manufacturing system, all the stuff like production line, the transformational aspects, what does that mean? The conversion of raw material into semi-finished products, the procedural aspect, where there are strategical level, where are the product planning at the production control, the operational level, and here all is supposed to, well, is analyzed the procedure of meeting the strategic plan objectives, which are the planning, implement, well, they plan, implement, and control and monitor the activities. So, first talking about the fusion welding operations, the fusion welding processes feature the joining of two mating substrates by creating a melting pool in their location. Example, the localized condensate location. Thus, knowing the substrate thermal properties, the thermal conductivity, the specific heat, thermal expansion coefficient, and density is important to evaluate the thermal effects on the weld quantity on the final extrude geometry dimensions. This is what fusion welding operations is about. You can see here the classifications of welding processes. There are fusion welding and solid state welding. We're going to focus on the fusion welding, and we're going to talk about the MIG. The MIG welding is typically applied in different locations with the body weld and through different implementations, such as semi-automatic welding operation, that is where here the electrode is controlled by a machine, but the movement is controlled by the operator by a person. The machine-based welding application, here the movement of the electrode is controlled by a machine. The automatic welding, the electrode and the movement is controlled automatically. Well, for example, in machine-based welding, it's necessary to do little settings, but in automatic welding, the movement and the electrode are controlled by automatically, and robot welding application, where are machines that they must not need any settings or any help. They do all the job by themselves. The MIG welding process can be controlled based on three different levels of weld variables. As defined as predefined variables, these are the ones that cannot be changed, like the electrode, the primary adjustable variables, that are the ones that can be changed in order to do the desired product. Which variables can be changed is the depth, the bed seam, and the width. So with changing these variables, the results of this is the travel speed, how much travel speed, how much arc voltage, how much welding current must be applied. These are the primary adjustable variables. And also the secondary variables, that are the distance to the welding and pull and its nozzle angle. These variables are important in the process. And the effect on the tip distance on the weld bed width. The tip is like the electrode, but in MIG. In this figure is shown the effect. You can see here if the arc length increases, the arc voltage must increase also to have a bed width, like the part that is welded. Here we have a representation with graphics of weld control variables and their effect in the penetration. Here in the penetration, if the welding current increases, also the penetration. If the arc voltage increases, the penetration increases. But as you can see here, like it stops increasing and it starts to not penetrate. And the travel speed. If the travel speed increases, the penetration also. No, the penetration it decreases. So sorry, I have problems with. Well, weld control variables and their effect on the bed width. The bed, if the weld current, as you can see, if the weld current increases, the bed width, it like increases, but it stops increasing and it starts to decreasing. If the arc voltage increases, the bed width increases also, as I explained it. If the travel speed increases, the bed width decreases. Here are the different shielding gas types, composition, and applications. This is the shield gas that is used in MIG. Here are shown, and the uses. It can be done a welding schedule. In this schedule, it can be recommended the electrode diameter, the welding current, the arc voltage, the wire feed, the travel speed, and the shielding gas flow rate. So you can have with this you have everything stipulated. That's the word, stipulated. So you follow always the same correct quantity of wire feed, of travel speed. So you always have that part well welded. The spot welding. The spot welding is the most used welding practice in automotive manufacturing. A completed body shell features at least 400 and 500 spot welds. And the resistant welding passes through different phases. That is the squeeze time. Here in the squeeze time, the piece is pressured by a mechanical, a mechanical pressure, and that's all. Here there is not heat added. Then the second phase is the welding time, and the current. Well, here the welding starts, and the current is flowing from the upper electrode through the lower electrode, and between here there is a part. Anyways, I will show a figure later. And the whole time here the pieces must be held, and the off time here the welding finishes, and in this stage you already have the piece welded. The quality of resistance. Here is the image that I said before. In order to know the quality, if the joint was good, it's necessary to see the nugget size. the diameter, the nugget location, the nugget shape, and the pitch. What is the pitch? The spacing between the nuggets. You can see here the nugget, the weld nugget is the one that is black, the representation of the spot welding. The spot welding data. The typical welding current is a range from 9 to 16 kiloamperes. The mechanical pressure is rated at 4 to 5 kilonewtons. The selection of the electrode tip is vital in ensuring the right level of current flow through the electrode into a material. The spot welding tips material. The materials are normally copper with alloying elements of chromium, cobalt, and beryllium. And the tip diameter, there's a formula. The D tip is equals to 0.1 plus 2 per T of the panel. And here are the spot welding defects. There is a schematic drawing if it is not well understood. There are different causes because anyways, even when the spot welding, it's a very good option for welding, it has effects. And spot welding settings, there is a formula based on the amount of heat per material needed to make the volume equal to that of nugget or that of the product of weld length by its cross section. As you can see here, the H is the heat, it's like 1, or L is the weld length, the V is the voltage applied, the I is the current, the V is the welding speed, and E is the welding efficiency. As an example, you can see here with a 1 millimeter thick steel with 500 amperes and current flow time of 0.1 seconds, using electrodes for 5 millimeters in diameter. Here is estimated the amount of heat generated on its distribution in the weld zone, and the effective resistance is the 200 micro-ohms. Here are applied these formulas. And also is used the heat required for diffusion. Normally this data is shown in tables. It's already calculated. The robotic spot welders. Here are all the advantages and the reasons why industries choose these robotic spot welders. They are very good, and for example, their typical available time for a spot welding robot for each vehicle shell is around 20 seconds, in which the robot applies around 6 spot welds in 6 different locations. An operator could not do this. This has a greater accuracy. This can be integrated into the production main control unit, and this can be controlled also by an add-on system. It can show when they are having troubles. The spot welding of the different panels requires a large number of degrees of freedom. What does that mean? That means that you can move to a lot of axes, not only X axis or the Y axis. They can move anywhere. The current spot welding, the welding robot integrates all the welding equipment, all have in one. The reliability is around 500 hours, and a welding robot hourly rate is approximated to $6 per hour. It's a lot. It's less than an operator. This is an image of a robotic spot welder. The adhesive bonding, this has been it's being more accepted in the automotive industry because it has a lot of advantages. The ability to join different materials, the compatibility or galvanic corrosion issues. What does that mean? That you can also use it with polymers, with plastics, and weld production light at low costs and easy to apply. It's very good. Adhesive material selection. Anyways, it's important to select the correct adhesive material, and the adhesive must withstand the conditioning cleaning processes The adhesives used in the body weld area are typically applied to surfaces covered with lubricants and oils. The adhesive viscosity should also be carefully selected because it affects the robotic application. If, if it is bad selected an adhesive material, it can affect a robot, or it can affect, for example, if you are painting a piece and there is an adhesive material, when you're painting that piece, that specific area won't paint because it has adhesive material. So the different types of adhesives here are shown: the elastomers, thermoplastics, and thermosets. The conclusion: the proposed calculations are correct because the electrode consumption is equal to the weld time multiplied by the feed rate, as in equation 3.10, and the weld time is given in equation 3.11, while the electrode volume is shown in equation 3.12, and the power consumption is described by equation 3.13. Here are the calculations that are made to have the correct amount of quantity of heat or voltage. So these were well applied in the welding schedule. The variable costs also were taken into account, and the fixed cost in terms of building maintenance and insurance and tooling investment, and the number of robots needed to complete the frame welding. The frame and the door process to both have the same methodology. For example, there I am showing the formula of number of vehicles per minute, and this formula was applied in both cases of the frame and in the door. And that's all. This is a bibliography. All this information I took from a book that is named The Automotive Body of Manufacturing Systems and Process. And that's all. Thank you.